My name is Karthik Prasad, and I'm a student at UC Berkeley, and for my BioE 147 final presentation, I'll be talking about a synthetic circuit that I call menopause, controllable estrogen delivery for postmenopausal women. So let's get right into it. So first off, my motivation. While I was studying for my MCATs, I realized that menopause impacts millions of people. In 1998, it was estimated that there were over 477 postmenopausal women in the world. And that was in 1998. It is projected to rise to 1.1 billion people by the end of the year 2020. Now, usually for me and for most other individuals, that number alone is enough to highlight a significant health concern worthy of your attention. However, there are funding sources and there are companies that need a little bit more incentive to go down this route. In terms of the market side, the global market for hormone replacement therapy, which is required for individuals who want to recover from this, the market is estimated to be at $15.1 billion, and it's expected to have a compounded annual growth of 8.2% over the next 7 years. Essentially, not only are a lot of people suffering from this condition, but the market in which you could enter through a potential cure or a potential treatment has the potential to be highly lucrative. So let's get into the biology of what is menopause and why is it so important. So below, as you'll see, is biology basics, what the estrogen cycle in the body usually looks like. Now, estrogen usually peaks during ovulation and sort of tapers down, but as you can see, it's always there in the body of most normal individuals. And it plays a very complex dynamics with other hormones such as luteinizing hormone, follicle stimulating hormone, FSH, and progesterone. For at least this circuit, we're not trying to replicate the very complex dynamics that's between all these compounds. Rather, we want to focus on estrogen alone and at least have a basal level of production, so that way the individual doesn't suffer from some of the other debilitating effects. So what happens in menopause? So this table right here shows you what happens in terms of at least the molecules in this condition. As you can see, and a little bit more clearly now it's underlined, that FSH dramatically increases, estradiol, which is estrogen in its biology form, dramatically plummets, and testosterone, interestingly enough, stays the same. This is where these key characteristics is where I take my motivation and justification for the rest of the project. So 3 things, if anything, to keep in mind about what happens in postmenopause is that you have high FSH, you have very low estrogen, and you have the same level of testosterone, roughly. Now, for at least my circuit, we'll be trying to produce something called aromatase. Aromatase is an enzyme that catalyzes the reaction of testosterone into estradiol. As you remember from the previous slide, testosterone levels stay relatively the same, whereas estrogen levels plummet. In menopause, the effects of not having aromatase limits the production of estradiol. So what we will be doing is trying to fill that gap of producing aromatase at a level that is therapeutic to the individual via a regulatory circuit that prevents any negative effects to the individual. So let's jump right into it. So these are my overall constructs. Let's just call them nodes A, B, and C. We'll be going more into depth into each of them, so no need to memorize everything that you see right here. A couple things to keep in mind is that there are a couple promoters which are constitutively expressed, and there are other promoters which are and have the capacity to be positively regulated. Now this is a bunch of information. Let's make it a little bit more easier to understand, a little bit more visually appealing. So here is the gene regulatory network of what I just previously showed. So let's focus each node at a time, and then I'll get into the specifics later on. So let's start with node A. So node A can have the ability to self-induce itself. It can also be inhibited by node C in 2 pathways. One of them can be stopped with the introduction of IPTG, which is a chemical compound that prevents LACR from operating, which binds to LACR. The second thing is that the anterior pituitary can stop the inhibition of node A. These are a couple things to keep in mind. The one thing I'd really highlight is that IPTG is going to be introduced to the system via a dosage. We are going to assume that the system starts when IPTG is high and continues from there on. IPTG, while normally not metabolized by the biology circuit, will be naturally cleared, so the levels will gradually decrease over time. This is important because it allows for a very controllable oscillation and a controllable duration of therapy. So let's break it down one note at a time. And actually, we're not going to start at either A, B, or C. We're going to start at the anterior pituitary. As you can see, I put up the GRN in the upper right-hand corner for you to easily visualize each node as we go through it. These are the equations demonstrating what happens at each point. The dashed lines mean that the compound has to diffuse from the point of location to another area. And at least for this model, and one of the advice that I got from an individual, is that diffusion in the system was best modeled by a two-part compartmental system with a fixed coefficient of diffusion from one compartment to another. Since inhibin and FSH are both peptide-based, we're going to assume that they have roughly the same coefficient of diffusion, though they'll be in the same order of magnitude. They don't have to be perfectly identical, but they'll be in the same order of magnitude. Inhibin has a unique property of restricting FSH production. This is just a biology construct. This is not something that we don't have to produce. It naturally occurs in the body. When inhibin goes high, FSH production from the anterior pituitary goes low. And this is one of the reasons I want to take advantage of this natural regulatory cycle, which is unaffected in postmenopausal women, by producing inhibin and allowing it to diffuse. So, inhibin goes from the area of location, node B, to the anterior pituitary. It limits FSH production, and that goes back and interferes with axon node A. So let's go to now node C. I call this node C because it's constitutively expressed. FSHR, which is a restriction enzyme that binds in the lack of FSH, LAC-R, which is very well known, TET-R, and ARAC-A, are all going to be constitutively expressed by this node. Below you can see the equations describing it, very straightforward. ARAC-C is not shown because it will be discussed later on in node A. So let's go to node A. So in node A, as you can see, there's a lot of stuff happening, but two things to keep in mind. This node will be activated when FSH is high and IPTG is present in sufficient levels. Then, ARAC will self-induce a promoter to rapidly increase the amount of aromatase, and then this will also produce ATC, which will go and inhibit the inhibitor for node B, essentially activating node B. So in summary, node A is activated when FSH is high and IPTG is present, and also it will start inducing node B. So now let's go to node B. Node B is quite simple. It only expresses inhibin. Inhibin is going to be expressed when node A is expressed. This will cause that protein to diffuse into the anterior pituitary, and like I said before, the anterior pituitary and that area is going to reduce FSH production and causing node A to shut down, because that means no longer FSH is high. So there goes your node A activation. All right, so with all these equations, we plugged it into a MATLAB simulation, as you can see here. Now the first time we ran it, it failed because we took all of our constructs from biologically relevant values and it failed. So unfortunately, we had to focus more on optimizing the transcription rates for the model specifically. So gradually by adjusting those terms, we were able to get a nice oscillation over a period of roughly 16 or so hours. While not ideal to the 12-hour cycle I'd like to have, it's still nice. So this way, as you can see, aromatase enzyme is produced and degraded in a very oscillating system. This is important for two levels. One, the oscillation prevents the cell from being overburdened by this synthetic circuit. Second, the oscillating circuit allows it to produce estrogen at a relatively stable level. There's no sudden sharp spikes once the oscillating system sort of stabilizes. But by playing with a couple parameters, we were able to find some really unique aspects about the system. So first off, FSHR and inhibin places a special periodicity limitation on aromatase production. By changing inhibin's rate of transcription translation, you can see the period in which this occurs either narrows or widens. And if you go all the way to one extreme, it just produces the entire time. This is important because we wanted to see if we could characterize and specialize the time it takes to produce. Next, we went and looked at the RAC promoter binding capacity and how it determines the maximum rate of production of aromatase. If we increase the transcription and translation of aromatase and the way it works, you see the ceiling of aromatase concentration dramatically increases. But there's one key aspect I want to draw your attention to. Because of the FSH and FSHR relationship, when this node is highly activated, it also produces a high amount of ATC. And this activates node B for longer, and it activates it for stronger. So the period changes. And this is solely because of that safety factor we built in. So this is something that I was not planning, but it just so happened that in the event of, say, a random mutation occurs in the synthetic circuit, and all of a sudden aromatase starts, this particular circuit starts producing at a higher rate, because it will also be producing ATC, this will prevent node A from being activated at a highly toxic level. However, one drawback is it doesn't limit the ceiling, so it could have an impact on the cellular burden, causing some adverse effects. So a couple of things, what did we learn? The biology terms were difficult to define. The cooperativity, the Hill dissociation constants, and the production of the enzymes and proteins were really difficult to characterize. But one thing is important, it was possible. And the safety factors that we designed worked. They limited toxicity and they prevented it from running the entire time, placing a huge burden on the cell. Moving forward, I'd like to characterize and work within the biology constructs. I'd like to identify promising cell types in which to put into. Current candidates include bone marrow because of their proximity to the central circulation, but also we can look in other avenues. We also want to simulate RNA dynamics and not take so many simplifications. We also want to look for hazards in the system. Potentially, if there's a mutation in one or two acute areas, we could create a runaway reaction which causes dramatic problems for the user. And we also, if all of this sort of checks off, it might be cool to attempt in vitro wet lab studies in just a petri dish and see what happens when you add one inducer, IPTG, and the entire system goes. Thank you. Here are my references. Here's a code that I worked on. If you want it, please feel free to ask. And thank you so much for your time.